which generates our entire vector space. So we'll say a basis for a vector space is a linearly independent set which generates that whole vector space. Or a basis for a subspace will be a linearly independent set which generates that subspace. So we'll be able to tie together this notion of generating sets and linear independence together, and this gives us a basis. But for today, we're talking about linear independence. So this is the definition of linear independence. Whenever you have to check if something's linearly independent, this is what you're doing, right? So you've got some set of n vectors, v1, v2, all the way up to vn, and we form the sum alpha 1 v1 plus alpha 2 v2 plus alpha n vn, and we set this equal to the 0 vector. And then if the only solution is this trivial solution, if the only solution is that all of these alphas must be equal to 0, then the set is linearly independent. Now, every year there are people who write down something in the test or the exam where they say that if this is the solution, then it's linearly independent. I mean, that's meaningless, right? This is always a solution. So it's not that this is a solution, it's that this is the only solution, right? So that's important. That's why that only over there is underlined. So linear independence is that this is the only solution. And then the second sort of part of this definition is linearly dependent sets. And that differs in that if your set is linearly dependent, so you've got v1 all the way up to vn, clearly this is still a solution, right? You could still set 0 v1 plus 0 v2 all the way up to 0 vn and add them together and you still get 0. But if there's another way of adding them up, you know, maybe it's 1 times by v1 minus 3 times by v2 plus 5 times by v3, and there's some way of adding them up, and you can find some of these coefficients, at least one coefficient, which isn't 0, then we say it's linearly dependent. So if there's only one solution, and it's the 0 solution, it's linear independence. But if this equation here has more than one solution, it's linearly dependent. So let's take a look at some examples. Yes?
Does that mean that if any of those vectors, v1, v2, are the 0 vector, then it must be...
That's an excellent observation, yes. If one of your vectors in the set is a 0 vector, then the set must be a linearly dependent set. And that sort of spoils the first example that we're going to look at. Somewhat. So we're going to say this. Consider so we're going to consider the singleton set. Singleton is just a fancy way of saying that it has a single element in it. So we've got a set S of one vector, v1. And the question is this set S, or when is the set S, when is S linearly dependent or when is a set linearly dependent or linearly independent? And does anyone want to make a suggestion now that we sort of have already seen the answer to this? Well, what we're really looking for is when can we find more than one solution what can we say about solutions to that equation over there? When is that going to have more than one solution, more than just alpha 1 is equal to 0? When v1 is equal to the 0 vector. If v1 is equal to the 0 vector, then you can choose, well, then you have an infinite number of solutions, right? Alpha 1 could be 5 or 10 or negative or 100, and that would still hold, right? So if you've got a singleton set, and the one vector in the set is the 0 vector, then we say that that set is linearly dependent. Otherwise, the only solution, if v1 is non-zero, the only solution would be that alpha 1 is 0, and then we have a linearly independent set. So let's write this down over here. So if v1 is the 0 vector, set is linearly dependent if v1 is not the zero vector, set is linearly independent. And let's just, make the more general remark over here, which was that any set which contains the zero vector is linearly dependent. Right, because you can always choose the coefficient in the sum. You've got alpha times by the zero vector plus a bunch of other things. And you can make all those other things equal to zero, and then you can choose any non-zero value in front of the zero vector. Okay, so any set which contains the zero vector will be linearly dependent. Let's take a look at another example, and this is not such a simple example. We don't have a zero vector. But you'll take 5 minutes to do this. Is the set S, and we'll have a set here of 3 vectors, 1, 2, 3, 4, 1, 5, 2, 3, minus 1, so is that set S over there a linearly dependent or independent set? I'll give you a couple of minutes to think about this. Let me just briefly outline what you should be trying to do. You want to write down a system of equations. It's going to be alpha times by 1, 2, 3 plus beta times by 4, 1, 5 plus gamma times by 2, 3 minus 1. And we want to check what the solutions for alpha, beta, and gamma are. And so the easiest way that we can do this is to write up an augmented matrix representing that system. Take your augmented matrix, Gauss reduce it, and after you've done the Gauss reduction, one of two things will happen. Either you'll do the Gauss reduction and you'll discover that one of your rows is missing a pivot. In that case, you've got an infinite number of solutions, and this will be linearly dependent. Or you do the Gauss reduction and you can Gauss reduce the left-hand side of the augmented matrix all the way down to the identity matrix. And if you do this, then you know that it must have exactly one solution, which is the trivial solution. You, in fact, actually don't have to Gauss reduce it all the way down to the identity matrix. You just have to Gauss reduce it far enough to tell that it's got a unique solution. So you only have to put it in row echelon form, not reduced row echelon form. But go ahead and try to do that. I'll give you a 2 or 3 minute head start, and I'll start writing things up. But I won't talk through it when I start writing it. what you should do. This is what you should do when you solve the problem. You start, and in fact, I mean, this very first line that I've written right at the top, maybe you don't need to write that down. Maybe you can see immediately what augmented matrix you need to write. But just for the sake of making this clear, what we're interested in is we're interested in checking if this is linearly dependent or independent. The definition of linear dependence or independence says that you've got to have alpha times by the first vector, alpha 2 times by the second vector, alpha 3 times by the third vector. You add that all up and it's supposed to be equal to 0. So I've just called them alpha, beta, and gamma instead of alpha 1, alpha 2, alpha 3. But that's what we've written up. That first line over here, this is the definition of linear independence or dependence, right? We have to determine whether or not alpha, beta, and gamma, the only solution is 0, or whether there's maybe a non-trivial solution. So underneath here, we've got the augmented matrix, right? Each row in that augmented matrix corresponds to one of the rows, one of the components in our vector, and each column corresponds to one of these. Each column here corresponds to one of these unknowns. Okay, so we do some Gauss reduction, and we don't have to do the entire Gauss reduction. It's sufficient that we Gauss reduce to this point over here. And having Gauss reduced to this point over here, what we realize is that we've got a pivot in each column, pivot in each row, equivalently in this particular case since it's a square matrix. But that means that there must be a unique solution, and the unique solution is that alpha is equal to beta is equal to 0. So at this point here, we can conclude that the only solution is the trivial solution, which in turn means that the set that we started with must be a linearly independent set. Right. So let's just say at this point, 3 unknowns and 3 pivots implies a unique solution. Alpha is equal to beta is equal to gamma is equal to 0, which means that S is linearly independent. All right. Let's just see if we can fit it. Yeah, there we can fit it all on one page. Is everyone happy with this example? You all understand what we've done and why we've done it? Okay, so let's keep going. And this is fact 1.17. It's actually a remark that I made yesterday, but we can write it up as a fact. And this is just saying that there's an alternative way of thinking about linear dependence and independence if you've got a set of 2 or more vectors. So let S be a set of 2 or more vectors. It has to be a set of 2 or more vectors. Okay, then saying S is linearly dependent is completely equivalent. It's exactly the same as saying that there's at least one vector in S which can be rewritten as a linear combination of some of the other vectors in S. Okay. Then S is linearly dependent if and only if, right? If and only if is basically, this over here is just an implication which runs in both directions. So S is linearly dependent if something, and S is linearly dependent only if something. Right? So S is linearly dependent if and only if at least one vector in S is a linear combination of the others. So we're going to try to explain why this is the case. And we've got two different things we need to explain here. Firstly, we've got to start with this set S, and we've got to say, well, if S is a linearly dependent set, then we can show that one of the elements in S can be rewritten as a combination of the others. We also have to start with S, where we know that one vector in S can be written as a linear combination of the others, and then show that it's linearly dependent. So we've got to move in both directions here because this is an implication which moves in both directions. So there are two different things we've got to show. So let's start by showing this direction, right? So we're going to start with a linearly dependent set. So let S, or S, S is linearly dependent. So what does it mean for S to be linearly dependent? Well, there is at least one non-zero alpha, let's call it alpha k, in this sum. There's at least one non-zero alpha k in this sum, right? Alpha 1 v1 plus alpha 2 v2 plus alpha k minus 1 vk minus 1 plus alpha k vk plus alpha k plus 1. Okay, I should have started this sum further off to the side. Alpha n vn is equal to 0, right? There's at least, okay, that's a really bad looking alpha. Yeah, that's a little bit better. If we write out this sum over here, because our set is linearly dependent, we know that there's at least one coefficient, call it alpha k, which is not 0. So this alpha k over here is not 0. The rest of them might all be equal to 0, but there's at least one over here which is not 0. We want to use this information to show that there's a vector which can be rewritten as a linear combination of the other vectors. So any suggestions for what we should do next? Maybe as a first step, which vector should we be trying to rewrite as a linear combination of the others? vk, right? We don't know anything else about any of the other vectors. The only vector we know anything at all about is vk. So if we want to write vk as a linear combination of the other vectors, what should we do? Okay, so some people are making appropriate hand gestures. We're going to take this term here across to the other side of the equality. And then, okay, let's do that, and then we can think about what happens next. All right, so we've got alpha 1 v1 plus alpha k minus 1 vk minus 1 plus alpha k plus 1, right? Okay, there's a gap here. vk plus 1 plus alpha n vn, that's equal to minus alpha k vk. So we just popped it across to the other side. What next? Divide by minus alpha k, right? We want to divide by minus alpha k because we want just to get vk by itself. And we know that we can divide by alpha k or by minus alpha k because we know that alpha k is non-zero, right? In general, we can't just divide by an unknown constant because that constant might be 0, or an unknown coefficient here. The coefficient might be 0. But we specifically said alpha k was the non-zero coefficient, which is responsible for making this a linearly dependent set. Okay? Okay, so we can divide through by minus alpha k. So we get minus alpha 1 over alpha k v1 plus, okay, and I'm going to skip all this nonsense in the middle, and we just go all the way up. Okay, I guess this would be a minus. This would also be a minus. Minus alpha n over alpha k vn is equal to vk. All right, and now we're done. We've shown that vk can be written as a linear combination of all these other vectors. All these coefficients here, they're just, coefficients. They're the appropriate scalars depending on what vector space we're working in. Is everyone happy with this first part of the proof? All right. So you can take a minute or two for yourself and try to show that it must be the case in the opposite direction. And basically the idea is right here, you just run it backwards. But if you start with one vector, which must be a linear combination of the other vectors in the set, show that you can find a solution to alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3 and so on. Show that you can find a solution where at least one of the coefficients is not equal to 0. All right. So the idea is basically exactly the same as the idea from the previous part of the explanation. We just sort of run it backwards, right? So we start now, instead of starting with a linearly dependent set, we start with a set where one vector, call it vk, can be rewritten as a linear combination of the others. So that's what we've got there. Alpha 1 v1 plus alpha k minus 1 vk minus 1 plus alpha k plus 1 vk plus 1, all the way up to alpha n vn. You add all of those together, you get this vector vk. So one of the vectors vk is a linear combination of all the others. Then we subtract that vector vk from both sides. And all that means is that we've got here now on the left-hand side minus 1 times by vk. And on the right-hand side, vk minus vk just gives you your 0 vector. And since there's at least one coefficient in this sum, which is not 0, it's right here, it's this minus 1, this meets the requirements for being a linearly dependent set. And now we're done. Are there any questions about what we've done here? Right. So I just want to make something very clear, which is that this over here is an alternative way of thinking about linear dependence and linear independence. But it is not the definition of linear dependence and linear independence. So if we ask you what the definition is, or if we ask you to check that something is linearly dependent or independent, you don't do this. You go back and you check the sum, alpha 1 v1 plus alpha 2 v2 plus alpha n vn equal to 0. You check what solutions there are to that sum. Right. So let's keep going. Let's take a look at some more examples. And I want to look... Yes, you have a question.
You say that you subtracted vk from the left side of the...
Yeah, from the left and from the right.
Then how come the vk is only being seen, like, why is it alpha 1 v1 minus vk? Why is it only the same?
Well, I mean, it should... You can put it wherever you want, right? You've just got this sum over here minus alpha k vk. And it makes sense. The natural place to put it is between the vk... Oh, there should be a minus 1 here. But the natural place to put this is just in between the k minus 1 and the k plus 1 terms. You could put it anywhere, but I mean, that's just the sensible place to put it. The indexes line up nicely. All right. So we're going to do some more examples now. And we're going to look at linear independence of sets of vectors, but the vectors are going to be functions. And so there's one small sort of addendum, one small note, one additional complication, if you like, that we have to just make very clear when we speak about linear independence of functions. And let me write it like this. When we say a set S equal, let's say f1, f2, fn. When we say that a set S is linearly independent or linearly dependent, we should always specify a domain, right? So we shouldn't just say this set is linearly independent or linearly dependent. We should say this set is linearly independent on R, you know, on the whole real, on all the real numbers. Or it's linearly dependent from 0 up to 2 pi, right? So we should always specify an appropriate domain. So when we say, that should be when we say, not we say. When we say a set S of functions is linearly dependent or independent, we should specify a domain. And what that means is that when we write down alpha 1 f1x plus alpha 2 f2x plus alpha n fn x equal to 0, we're looking for values alpha 1, alpha 2, all the way up to alpha n. We're looking for these values that are going to work for every x in the domain. So we want to write this down, and this should be for every x in the domain. So it's not just enough to think about, oh, we're interested in finding one particular point. That's not what we were doing here. We want some values of alpha 1 and alpha 2 and alpha 3 and all the way up to alpha n that make this true, the same values of alpha 1 to alpha n, that make this true for every point in the domain. And with that in mind, let's take a look at some examples where we try to decide whether or not particular functions, particular sets of functions, are linearly independent. And we'll see later on in the course that there's a better way to do this. For now, we're going to use the definition, but there is a quicker way, or a nicer way of checking whether or not sets of functions are linearly independent or dependent. It's called the Wronskian. It's a determinant of an appropriate matrix, but we'll get to that in a couple of weeks' time. Right. So here's the first one: is this set is S equal to x squared x1, right? X squared x1, is this a linearly dependent or independent set of functions? And I guess I've just done a thing that I told you shouldn't do. Linear independent or dependent there on R, right? I suppose if they don't, if there isn't a domain which is specified, I suppose you just take the largest possible domain that you can. The question is now, are these functions linearly dependent or independent? So what we're trying to do is we're trying to solve the following. We want to know, what are the solutions to this equation? What are the solutions to alpha x squared plus beta x plus gamma times by 1 is equal to 0? So we want to solve, and this must be true for every x in our domain, right? So does anyone have suggestions for how we might go about trying to find values of alpha, beta, and gamma that solve this? I mean, it's obvious that alpha is equal to 0, beta is equal to 0, gamma is equal to 0 will solve this. But how do we know that that's the only solution if we want to show that this is linearly independent? Or how do we find some other combination for alpha, beta, and gamma that will make this add up to 0? So the point is, linear independence or dependence of functions, we're interested in the question of whether or not we can find alpha, beta, and gamma values that don't change. Can we find alpha, beta, and gamma values that work for every value of x on the interval? Okay, so maybe I'll start us off, and you can use this first idea to find the rest of the constants. So we're looking for values, alpha, beta, and gamma, that satisfy alpha x squared plus beta x plus gamma x is equal to 0 for every value of x in the reals. So in particular, we should be looking for values, alpha, beta, and gamma, that satisfy the equation alpha times by 0 squared plus beta times by 0 plus gamma is equal to 0, right? If we want this to be true for every value in x, every value x in the reals, it should be true for particular values of x. So if x was equal to 0, we'd be looking for values that satisfy alpha times by 0 squared, which is 0, plus beta times by 0, which is 0, plus gamma is equal to 0. Okay, so that we get straight away gamma is equal to 0. And maybe you can choose some other appropriate points and try to find the other values for alpha and beta.
Could you use the quadratic formula where x equals minus b plus minus beta squared?
So that'll find the roots of this equation.
Yeah.
Right, so that'll just tell you that for certain values, if you set x equal to certain values in terms of alpha, beta, and gamma, this is equal to 0. So that just tells you about this quadratic being equal to 0 at a particular point. It doesn't tell us about, we're looking for something which is going to be 0 everywhere.
Yeah, I was just thinking because x equals 0 when that equation is satisfied.
X equals 0 in this equation is satisfied.
So the quadratic equation would not work.
No. In some sense, the quadratic equation is... Yeah, the quadratic equation assumes that this is not happening everywhere and just finds particular points where it happens. We want to find... We're assuming that it does happen. Okay, so did anyone else choose a different value of x? 1. Okay, 1 is a good choice because if x is equal to 1, we get alpha plus beta is equal to 0. And another value of x? Minus 1. Okay, x is equal to minus 1. We get alpha minus beta is equal to 0. And together, the sum of two numbers is 0 and the difference of those numbers is 0. Okay, the only way that this works is if alpha is equal to beta is equal to 0, right? So what this tells us is that x squared and x to the 0, the constant 1, these are linearly independent functions. There's no way to add up 1's and x's in any combination that is equivalent to x squared. And sort of geometrically, that makes a lot of sense. You can add x's to 1's as much as you like, and you just get a straight line, right? You can fiddle with its intercept and you can fiddle with its slope, but it's a straight line. But x squared qualitatively looks very different. X squared is a parabola, right? So this makes a hell of a lot of sense. These three functions are linearly independent. So S is linearly independent, and that makes this next problem a little bit easier if we know that x squared and x and the constant function are linearly independent. So we've got three polynomials here, x squared plus x minus 1, 2x squared plus 3x plus 1, and x squared minus 4. And we want to check if these are linearly independent. And, sorry, I'll be with you in a moment. Again, I've forgotten to specify a domain. What about S on R? Yeah, because you have a question.
So please explain again why we're doing those substitutions.
Okay, so what we wanted to do, we wanted to find values of alpha, beta, and gamma so that alpha x squared plus beta x plus gamma x is equal to 0 for every value of x in the real numbers. Okay. So in some sense, what we have here is we've got three unknowns, alpha, beta, and gamma, and we have an infinite number of equations, right? Because that equation should hold no matter what value we substitute in for x. So you've got three unknowns, infinite number of equations. That's too many equations, right? So the easiest way to solve this is to say, well, I don't want an infinite number of equations. Why don't I just look at three equations? And I can find three equations really easily simply by choosing three particular values of x. So I've chosen these three values of x, and I've chosen these three rather than 5 and 100 and negative 20 because these make the manipulations much easier. But alpha x squared plus beta x plus gamma is equal to 0, that must be true when x is equal to 0, if it's true for every x. So if it's true when x is equal to 0, we get gamma is equal to 0. And if it's true when x is equal to 1, we get that equation. X is equal to minus 1, we get this equation. And together, these three equations and three unknowns give us a unique solution, which is that alpha is equal to beta is equal to gamma is equal to 0. All right. So let me explain. We won't have time to do the whole problem. You can do it. You can finish it off as homework. But let me explain how you would set this problem up using what we've just discovered or what we've just learned about x squared x and the constant function. what we're interested in is alpha x squared plus x minus 1 plus beta 2x squared plus 3x plus 1 plus gamma x squared minus 4 is equal to 0, right? And we can rearrange this. I'm just going to group all the x squareds together and all the x's together and all the constants together. So if we rearrange this, we get alpha plus 2 beta plus gamma x squared plus alpha plus 3 beta x plus minus alpha plus beta minus 4 gamma is equal to 0. And we have just in the previous line, sorry, not in the previous line, just in this previous problem, the one with x squared, x, and 1, we've just said that x squared and x and 1 are linearly independent of each other, which means that each of the coefficients here must individually be equal to 0, right? So we can say that this over here must be equal to 0, and this over here must be equal to 0, and this over here must be equal to 0, since x squared, x1 linearly independent. And this means that we can write down an augmented system. 1, 2, 1 should be equal to 0. 1, 3, 0 should be equal to 0. Minus 1, 1, minus 4 should be equal to 0. We can write down this augmented system, and you can Gauss reduce this. And either you're going to Gauss reduce it, and it will Gauss reduce on the left-hand side to something which has got 3 pivots. In that case, it's got a unique solution. If it has a unique solution, the only solution will be that alpha is equal to beta is equal to gamma is equal to 0. And then we know that it's a linearly independent set of functions over here. On the other hand, you might be able to find, or you might find that you Gauss reduce and you only have 2 pivots or 1 pivot. So you've got an infinite number of solutions, which means that your set is linearly dependent. And if your set is linearly dependent, what you can do, maybe to convince yourself really that it is linearly dependent, is try to rewrite one of those up there as a linear combination of the others. Okay. So I think that's everything for today, and I'll see you tomorrow. Or I'll see you in the TUT this afternoon.